Hey guys, in this video we will discuss LeChateliers' principle and more specifically how an equilibrium reaction responds to the disturbances like changes in reactant or product concentration. If we consider a reaction that is at equilibrium, we know that the rate of the forward reaction is equal to the rate of the reverse reaction. Remember that at equilibrium, Q is equal to K. If the equilibrium reaction is somehow disturbed by, say, a change in concentration of a reaction component, this will change the rate of the forward and reverse reaction. Since the rates are no longer equal, the system is no longer at equilibrium. At this point, Q does not equal K. However, LeChatelier's principle states that the system will shift to minimize the disturbance and regain equilibrium. It is our job as chemists to understand how the chemical reaction reacts to specific disturbances to regain equilibrium. As previously mentioned, the changes in concentration of reactants and products disturb a system at equilibrium. Additionally, changes in the equilibrium system's volume and subsequently pressure, since the two are inversely proportional, may induce the shift to regain equilibrium. A change in the equilibrium temperature can also affect equilibrium, and unlike other disturbances, it changes the equilibrium constant. In this video, we will discuss in further detail the effects of concentration change to the equilibrium system. We know that when a system is disturbed, it is no longer at equilibrium, and therefore Q does not equal K. In order to understand how the system will minimize the effects of the disturbance to regain equilibrium, it is important to understand the value of the reaction quotient Q produced from this disturbance. If the disturbance results in a Q that is less than K, this indicates that the current concentration of products is less than the equilibrium concentration of products. Therefore, to regain equilibrium, the reaction must shift right to increase the product concentration. In the opposite scenario, where the disturbance results in a Q that is greater than K, the product concentration is larger than it would be at equilibrium, while the reactant concentration is smaller. In order to minimize this disturbance, the reaction must shift to the left to reestablish equilibrium. Let's take a closer look into what types of concentration changes would cause each scenario. For example, in a situation where Q is greater than K, the disturbance could have been caused by either an increase in product concentration or a decrease in reactant concentration. Either of these concentration changes would cause the concentration of the product to be larger than the reactant, meaning that the Q is greater than the K. In order for the system to regain equilibrium and minimize this disturbance, the reaction must shift left in order to reestablish equilibrium of the system. Oppositely, if the disturbance causes Q to be less than K, this means that either the reactant concentration was increased or the product concentration was decreased. In order for the system to regain equilibrium and minimize this disturbance, the reaction must shift to the right in order to increase product and decrease reactant to their equilibrium concentrations. So let's try an example. Now, although we can't see the balance beam animation, when we're practicing this problem, you can use your hands to represent the chemical reaction balance beam. Your left hand represents the reactants and your right hand represents the products. Remember that a balance beam must start at level, but you can move your hands to mimic the type of disturbance occurring. So let's try these examples. If we consider the following reaction at chemical equilibrium, 2BrNO forming 2NO gas plus Br2 gas, we're asked what is the effect of adding additional Br2 to the reaction mixture. So in this case, we're adding additional products. So get your balance beam out and you'll see that your product side is actually going to be heavier. And therefore, to regain equilibrium where our balance beam is level, we must shift this reaction to the left in order to regain equilibrium. The next question asks us what happens if we add additional BrNO to the reaction mixture. Okay, well, if we have our balance beam, we can feel that it's getting heavier on the reactant side. So this is going to be the opposite case. Our reaction is going to have to shift to the right in order for the reaction to regain equilibrium. Finally, if we remove NO from the reaction mixture, we're removing a product, and therefore the right side of our balance beam should be getting lighter. and therefore, similar to adding the additional reactant as in the previous problem, we're going to have to shift the reaction to the right in order for it to regain equilibrium. So overall in this video, we have learned that LeChatelier's principle states that when a chemical reaction is at equilibrium and it is disturbed, the reaction will shift to regain equilibrium. We specifically looked at how concentration changes of reactants and products will disturb a system. In the next video, we will look more closely at the chemical reaction's response to changes in volume, pressure, and temperature.